Okay, so we were looking at ideal gases and the compressibility factor. In this lecture, we will look at a problem on compressibility factor and we will be looking at equations of state. So let's start with the problem on compressibility factor. It says what is the percentage of error involved in treating carbon dioxide at 3 megapascals and 10 degrees Celsius as an ideal gas. So it is asking us the error. If we think about it, the closer Z is to 1, the closer the gas is to ideal behavior. So if we are able to find Z of CO2 at the given pressure and temperature, then we can relate it somewhere to the error in treating the gas as ideal, right? Then we can find error, right? So we will be using this table that we discussed earlier, and you can see that to use this table we will need to find the reduced pressure and the reduced temperature. After finding the reduced pressure, we will be able to see where on x-axis our vertical line intersects the reduced temperature curves. So let's do that. If we remember, the reduced pressure formula was P given by Pc and our reduced temperature formula was T given by Tc. So using table A.2, we can see that Pc for CO2 is 7.38 megapascal and Tc for CO2 is 304.1 Kelvin. So our PR becomes a P given, which is 3 megapascals, divided by Pc, which is 7.38. So we get 0.406. Similarly, TR is T given, which is 10 plus 273. Remember, everything in Kelvin upon 304.1. We're doing this because we want in Kelvin, not degree Celsius, because this is also in Kelvin. Regardless, always convert temperatures to Kelvin when doing calculations with it, because otherwise your answer will 100% be wrong. Even if the value in table is given in degree Celsius, if you need to use that in a question, I would highly advise you to convert it into Kelvin during your calculation part. Right. With that being said, after calculating this, our TR comes out to be 0.930. So let us learn how to use this table to estimate Z for CO2. Going on the x-axis here, we can see our PR is roughly 0.4. So 0.1, 0.2, 0.3, 0.4. Notice that this x-axis is logarithmic, which is why the spaces between the consecutive divisions are not constant. However, that is not something too important, as all we have to do is find the point that we are looking for. Again, 0.1, 0.2, 0.3 and 0.4. So this is the line that we will find the intersection of the curve with. Now we want TR curve at 0.930. So we can see that the TR curve for 0.9 is here and 0.95 is here. Seeing as our value is somewhere between these, we are free to choose either the 0.9 curve or the 0.95 curve. There will be a certain degree of error to this because we don't know the exact curve for TR at 0.93. So I will be choosing the curve at 0.95 and I will be highlighting it. So we can see where it intersects. 0.95 somewhere over here. So if we take this value on the y-axis, we can see our Z comes to be around 0.82, or you can say 81 also, 83 also. This much accuracy is generally considered acceptable. The important thing is you must learn how to read this table, right? So now we have obtained our value of z. Now the formula for error involved in treating it as ideal gas is given over 1 minus is given by 1 minus 1 upon z. Again, I don't know how I got this, but you must remember this. I think it will come out to be close to 0.22. Error is also given by V actual minus V ideal by V actual. This formula 1 over 1 minus z was probably made from this, because this formula makes sense, because this is how you calculate error for any general thing, right? The actual value minus the ideal value upon the actual value, right? So anyways, you can remember both of these formulas because they will be helpful. So that is how we use this table to find the value of z.